Let's start module number 14 on Amazon Cloud Architecting certification. Module number 14 talks about building serverless architecture and microservices. It's a knowledge check. We'll go through the right answers and wrong answers, and we'll try to find the justifications for that. So question number 1 says that a solution architect wants to propose a microservice architecture on AWS to management. Which serverless computing benefits should they include in the proposal? So there are 3 answers for this one: pay for value services, continuous scaling, and built-in high availability. Now try to understand that serverless computing on AWS gives you 3 big advantages. You only pay for what you use, the system automatically scales with demand, and high availability is built right in. You don't have to manage and provision the servers. AWS handles all that for you, so you will save a lot of money, time, and operational effort while your application stays reliable and responsive. Now let's see the other options like predictable performance. We didn't select this option since that's not a typical serverless benefit, because performance depends on workload and concurrency, not fixed infrastructure. We are not going for the second option called lessens the amount of server maintenance. While true to some extent, the key benefit is no server management at all, not just less. And we are not going for full control over runtime environment. In serverless, you don't control the runtime operating system. AWS abstracts that away to simplify the operations. Question number 2 says a developer needs to create and deploy simple web form to capture employee commute information for the company internal employees website. Which is serverless solution for creating a simple web form? So the right answer for that one is to host a static website in a Amazon S3 bucket, use an Amazon DynamoDB table and Amazon API gateway and Amazon Lambda function to interact with the database. This is the true serverless setup. S3 serves your static web assets like HTML and JavaScript. API gateway would expose the API endpoints. Lambda runs your backend logic when needed, and DynamoDB would store the data. No servers to manage, fully scalable, and you only pay for execution time. Now let's try to explain the other options. First of all, they were saying host website asset in a container, in an Amazon Elastic container cluster with EC2 instance nodes, use Amazon DynamoDB table, and use server-side script to interact with the database. That's wrong because that involves managing EC2 instances, so it's not serverless. We didn't select the second option, which says host website assets in container in Amazon Elastic Container Service, cluster with Fargate nodes, use Amazon RDS database, and use server-side script to interact with the database. Fargate reduces management but still runs containers, so it's also not fully serverless. And we didn't select the last option, which was like host static assets in Amazon S3 bucket, use Amazon RDS database, and use Amazon API gateway and AWS Lambda function to interact with the database. Reason is that RDS requires continuous provisioning. It's not serverless like DynamoDB. Now question number 3 says that why would a solution architect recommend to use microservices architecture? There are 2 answers for that: solves a specific business problem and independent from the components. Microservices are designed to handle one specific business capability and to do it well. Each microservice works independently, so teams can develop, deploy, and scale them separately without affecting others. This independence gives flexibility and resilience. Now, we are not going for HTTPS communication. That's just how services talk, not why we use microservices. Open source code is not an option since microservices can use open or close mode. That's unrelatable. And then we didn't select industry standard interfaces. It's a good practice, yes, but not the reason to use microservices. Question number 4 says, which scaling configuration does a team lead need to apply and accomplish Lambda function scaling? None, because the AWS Lambda service scales functions automatically. Lambda automatically scales out by running multiple instances of your function in response to the number of events. You don't configure scaling groups or parameters. AWS does it for you behind the scenes. Now, we are not going for the first option which says configure the auto scaling parameter in the function configuration. Lambda doesn't need manual scaling configurations, and we didn't select the second option which says provision in a function instance to meet the maximum predicted load. The reason is that you don't pre-provision Lambda functions, and we didn't select the last option which says launch functions in auto scaling group, because auto scaling is for EC2, not for Lambda. Question number 5 says a solution architect has to use custom library in an architecture that uses Lambda function as the compute option. Which Lambda feature should be used for optimal function performance or deployments? The answer for that is Lambda layers. Lambda layers let you package libraries, dependencies, and even shared code separately and reuse them across multiple Lambda function. It keeps your deployment cleaner and faster. So we didn't select Lambda functions URLs. Reason is it's used to create an HTTPS endpoint, not for code packaging. We didn't select Lambda destinations because it handles the successes or failures routing after execution, not libraries. And we are not going for Lambda triggers because define what invokes a function, not how it's built. Question number 6 says, which of these statements is true for software packages as a container? So standardized portable application code packages that contains code and code dependencies. A container is run by container engine. A container does not include a guest operating system. So containers build everything that your app would need, codes and dependencies in a portable package. They would run on a container engine like Docker, sharing the host operating system kernel, so they are lightweight and fast. We are not going for the first option, which says that portable application code package that contains code and code dependencies. A container is run by a hypervisor. A container includes a guest operating system. The reason is that describes virtual machines, not containers. And then the third option, which says portable application code packages that contains code and code dependencies. A container is run by a hypervisor. A container does not include a guest operating system. Still inaccurate because hypervisors are for VMs, not containers. And we are not selecting the last option, which says standardized portable application code packages that contains code and code dependencies. A container is run by the container engine. A container includes a guest operating system. Again, that is a virtual machine, not a container. Question number 7 says, which is the most effective container deployment using Amazon Elastic Container Service? Containers when refactoring a monolithic application to use a microservice architecture. Creating a service that each provide a distinct function of the application and run each service in a separate container that Amazon ECS manages is the right answer. In microservices architecture, each service handles one responsibility and runs on its own container. ECS manages these containers efficiently, giving isolation, scalability, and fault tolerance. So let's explore the first option, why we didn't select it, like port the application to the new image and run it in a container that Amazon ECS manages. That's just rehosting, not breaking into microservices. We didn't select the second option, which says create services that each provides a distinct function of the application and run multiple services in a single container that ECS manages. That's wrong because that defeats the purpose of microservices. And we are not selecting the last option, which says refactoring the application and centralize common functions to create a small code print. Centralization goes against the microservices model. Question number 8 says an environmental science organization wants to provide HTTPS read-only access to its sensors data Amazon DynamoDB database. The user usage pattern is intermittent with 68% idle time per month. Which solution is the most cost efficient and secure with the least amount of operational maintenance? So the right answer for this one is create a public interface by using Amazon API Gateway with Lambda function accessing the DynamoDB sensor database. The serverless solution minimizes the cost maintenance. API Gateway handles HTTPS, Lambda would execute on demand, and DynamoDB would store the database. You only pay when it's used and idle time costs nothing. So let's explore the other options. For example, the first option, which says to create a web proxy server on Amazon EC2 instance in an auto scaling group connecting to the DynamoDB sensor database, which is served by an elastic load balancer. It adds unnecessary management and cost associated to that, so we'll not select that. The second option is create user account in organization system to allow direct access to the DynamoDB sensor database. It exposes the database and is a risky solution as far as the security is concerned. We are not going for the last option, which creates the microservices architecture by using Amazon Elastic Container Service connecting to DynamoDB sensor database. It's more complex and costly than needed for read-only access. Question number 9 says which workflows are suitable to implement Amazon AWS step function when the goal is to implement the solution to reduce the operational overhead? There are 3 answers for this one. First is to implement manual approval in security incident response workflow. Second is update the inventory and run a shipment workflow when the consumer purchases an item on an e-commerce site. Third is coordinate multi-step analytics and machine learning workflows. Now, AWS step function are ideal for coordinating multi-step processes, approvals, orders fulfillment, data pipelines, machine learning workflows, anything requiring sequential logic across multiple AWS services. Now, let's see the other options. For example, the first one, which says deploy different kinds of infrastructure that are based on environmental variables. That's handled by CloudFormation or CDK, not a step function. So we'll not select that. And then if we'll see the option of send message to multiple Amazon EC2 instances when file is created or modified in Amazon S3 bucket, SNS or SQS would be better in this case. And then we are not going for the last option, which says notify group of email addresses when the cost for an AWS account exceeds the threshold. That's CloudWatch or budgets, not step functions. And finally, the last question, a developer wants to implement a manual approval step using the AWS step function state machine. The manual approval state has to pause until a notification of approval or rejection is received from a approver email, which would be implemented in the step function state machine. So the right answer is a task activity state with an activated wait for callback parameter. For manual approval, the state function pauses execution until an external signal like an email approval sends a callback token. That's done when a wait for callback is configured in a task or activity state. If we look at the other options, which says a map state with automated callback parameters, the map is for parallel interaction, not for approvals, and a map state with an activated wait for callback parameter. Maps isn't designed for external approval awaits, and then a task or activity state with automated callback parameters. Automation won't pause for human input. So that was our module number 14, which talks about building serverless architectures and microservices.